All right, how's it going?
It's taking up 72 hours to get.
Not so good.
It's 72 hours.
Actually, it is Friday.
It is Friday.
Oh, I must turn that
We're
off.
having a cookout on the softball field later. I'm pretty excited about
That
that.
sounds like fun.
Yeah.
Cool.
Then we're going to the football game. Anybody here play football?
We're in the possibility yet.
I have played football in the past.
Retired.
What does that mean?
Hi.
Why? Just because we're.
Grace even told a riddle just to stall for you.
I just.
Questions on anything?
That's how
We could spike it.
that's how
No, there are no questions.
There are no questions? All right. Well, let's go on to new stuff today. That's exciting, right? New stuff?
Yes.
Yes? I think it's exciting. All right.
What was the
Good.
homework before we start?
What? No.
Can we work on 2.19 together?
No. No.
2.18.
No.
What? Yep. I can teach everyone, don't worry.
Teach us what?
1.19 or 2.19.
Hey, you got cheap.
Do you want me to? I can write it on the board.
No.
I need help.
You stalled long enough, Grace.
I need help. I need
I want to
help.
show everyone that Haley taught me how to do
I
it.
need help. Can you show me right?
Hey, Dr. Go, I have a serious question now.
See, I didn't talk.
I don't believe you.
What do you think about the Bears-Packers game last night?
I didn't watch the Bears-Packers game last night.
That's not
You didn't miss much.
From what I saw from the score, I
I'm
missed
still
much.
heated currently about the game, so let's not go there.
You just watched Mitch Trubisky play about as well as you would expect Mitch Trubisky to play.
Yeah.
He literally should.
I don't know
All right.
who I was sitting in the room watching with a Colts fan and a Bears fan. I didn't know who I felt worse for, honestly.
All right, so let's say you had a six-sided die. Did I actually hit start on this? Now that I'm thinking about it. Yeah, I did.
I thought we were just going to start a YouTube video just so
So a six-sided die is thrown. And I ask you, what is the probability that the result is a 2? That seems like a straightforward enough question, right? What would you tell me?
1 and 6.
1 and 6, right? Good. So that one's not too bad, right? You know that it's 1/6? We agree?
Yes.
Okay. What if instead that you already know, what if you know for certain that an even number was rolled? Now what's the probability? Okay, good. Good. So you know it's 1 out of 3, and why did you say it was 1 out of 3, Grace?
Because there's 3 even numbers and a 6-sided die.
Good, cool. So if we know ahead of time that you rolled a 3, or you rolled a new number, sorry, there's only 3 possibilities that you could have possibly rolled now, correct? So the probability that you actually rolled a 2, knowing that you already rolled a 3, I think you're saying 3 because of the 3 I just threw it down. The probability you rolled a 2, given that you had rolled an even number, the fact that you know that you have an even number already rolled, makes the probability higher. You got a 1 in 3 chance of having rolled a 2 rather than a 1 in 6 chance of having rolled a 2. So you've got additional information that has a potential for changing the probability. This is what we mean by the conditional probability idea. We're given more information. Okay? So when we do the definition here, the conditional probability of the event A given event B. Okay? So we're going to write down the formula here for a second, but let's think about what this means. We're calculating the probability that A happened, first and foremost, right? So probability that A happened, but we're given additional information that some other event B happened. Okay. So the way we read that is it's A given B, the probability of A given B. The way we calculate it is now, well, the notation looks like this. So we still use our probability function notation, the P. Probability of event A happening. We read the vertical bar here as given. And then B happens. That down. Okay. All right, so how do we calculate this? Well, instead of working with the entire sample space, we're only working with the fact that B happened. Okay? So we can think of this given information as changing the sample space. So instead of dividing by what typically would be the probability that the sample space happened, or just had a 1 there, on the bottom, we're going to have the probability of B. So when you're doing the conditional probability in the denominator, you're going to have the probability that B happened. Okay? Now, in the numerator, we are going to think about the probability of A happening, but notice that we said that B already had to have happened. So in order to get the probability of B given, probability of A given B, we have to know that both A and B happen. They have to happen at the same time, right? I can't have A happen if B can't happen at the same time. So for example, if I would have said, what's the probability of rolling in a 2 given that you rolled an odd number, you would have told me the probability was, what? 0. Because it's impossible to roll a 2 if you already have rolled an odd number. Right? So it's impossible for that result to be a 2 if you know that the result was already knew the result was an odd number. So the numerator of this becomes not just probability of A, but probability of A intersect B. So this is your conditional probability formula. A lot of times, or oftentimes, maybe I shouldn't say a lot of times, but oftentimes you might want to write this as a product statement rather than a division statement. Oops. So if I multiply both sides by probability of B, I get this statement. Notice that we could also swap this around. Notice that the probability of A intersect B is the same thing as the probability of B intersect A. So I could also write this as the probability of A and then the probability of B given A. Just swapping the roles of A and B in the formula. Okay? So both of these expressions on the right are equal to the probability of A and B. It doesn't matter what given information you're given. That was kind of weird, but what the given information is, I guess I should say. This becomes important in what we're going to do in section 1.6 in particular. And you'll calculate in this fashion. Being able to reverse these roles. So let's go back to the example. We had the probability, let's say that, let's write it this way. The event A was rolling a 2. The event B is rolling an even number. And let's see how the formula works in this case. So we said we wanted to do the probability of A given B, right? The probability of rolling a 2 given the fact that we had an even number. What? So the formula says that's the probability of A intersect B over the probability of B. But just the way, I think the helpful way to remember the division formula is that whatever's on the right, whatever looks like it's under the bar here, is under the bar here. It's always intersection on top. It's a matter of remembering which one goes on the bottom. Yes?
Can you explain again why it's the intersection on top?
On top? Because I need to know, I want to know the probability that A happened, but I already know that B had to have happened. So they both had to happen at the same time.
Okay.
So that's why we're doing the probability that they both happened at the same time. I need A and B to occur in this case. That's why I have the and on the top. All right, so let's think about this. Well, we already know the probability of an even number. You already told me that a minute ago. What is the probability of rolling an even number? 1/2, right? We agree with that? So let's think about the top. The top says the probability that you rolled a 2 and you rolled an even number. Well, a 2 is an even number, right? So the probability of rolling a 2 and an even number is the same thing as rolling a 2. So that probability is 1/6. And notice that we get the same answer when we simplify as we reasoned out before. We get a 1/3. That make sense? All right. So let's see if we can start putting this to work. Let's see if we can just do this with the context of the formula. So let's look at that sheet that did I hand out sheets to you already? Yes, I did. Anybody needed one? Anybody not get one that I handed out at the beginning of class? Marshall did not get one. Let's look at, I want to look at 3.3 on that sheet. You're given some information. Probability of A, I'm so not going to write squared off brackets. It's annoying. Probability of A is 0.3. Probability of B is 0.2. Probability of C given A is 0.6. Probability of C given B is 0.8. And we know that C intersect A and C intersect B are mutually exclusive. What does that mean again? Cannot occur at the same time. So if I'm doing the probability of either of those two events, what does that tell me? If I want the probability of C intersect A or the probability of C intersect B, what does that tell me? There's 0, right? Now what's it look like? Okay, good. No, I wrote a 6. Oh. There we go. Wonderful. Cool. All right. We agree? All right. What is the problem asking for now? The problem asks us to compute that, big long thing. Okay. So we have probability of C intersect A union B. Oh, wow. That sounds like fun. All right. Well, let's see if we can start simplifying some things. I think this one is helpful to, if we're going to do this with formulas, I think it's a little bit more helpful to simplify the set theory here before we try to break anything apart. So remember that with some set theory ideas, we can distribute the intersection over the union and rewrite this as probability of C intersect A union C intersect B. You can check that works with a Venn diagram if you'd like, or a set element set argument, subset argument. But that's basically, think about it as a distributive law for sets. The intersection distributed over the union, like so. And you could also do it if you had it reversed. You could do the union distributing over the intersection. It works the same way. Yes. So isn't it just 0? Is it 0?
0 is 0.
Well, I think we need to do one more thing, don't we? Well, those are empty, aren't they? Well, I said they're mutually oh, I'm sorry. I wrote the wrong thing. That's not what I mean. This is not what this says. They says those two. We wrote this as, this is not right up here. Let's try that again. This is not correct. It's a good thing I spent 10 minutes writing a 0. Let's go back to this statement before I get rid of it. It's good. I made an error. That's okay. It happens. Let's go back to this. What does this statement really say? If I think about its probability, does it say that these two events are mutually exclusive? This would say that C and A are mutually exclusive, and C and B are mutually exclusive, right? Right? So that's not what we mean. Right? What do we mean instead? We mean the probability that C intersect A intersect C intersect B is 0. That's what we mean. That's what it would mean for those two events to be mutually exclusive. Everybody see the difference? Okay. Well, now I'll actually solve a problem here. So let's go to this union again. How would I break up this union with our properties for our probability function? How do we break that up? You mean? No, well, yeah. So we just need to add them, right? You said union. And then subtract. It's the same thing. I'm unioning two numbers together. Okay. What do I subtract off? Something gets subtracted off in general. Anyone? What gets subtracted off? You mean the intersection? It's a Friday. Yeah, so in this case, we wouldn't need, in this particular case, we didn't need to worry about the intersection because why? What are we given? They're mutually exclusive, right? So that probability on the end, we already know that this piece is equal to 6. I mean, 0. Right? We already know that part's 0, correct? Okay. So in order to figure out the probability that we want, we need these two probabilities, right? The probability of C intersect A and the probability of C intersect B. Notice that we haven't done anything new yet, right? We haven't used the new formula that we just talked about. So there must be something that involves the formula. So how are we going to use the information that we're given in order to get these two pieces?
Intersection formula you gave us.
Okay.
So we do probability of C intersect A equals probability of C times the probability of
Okay.
probability of C intersect A.
Okay.
Or C
Okay. Okay. So if I want probability of C vertical line A, what needs to go in that first set of parentheses? Yeah, it has to be the A, right? Think about it this way. At least this is the way I think about it to keep it straight. I like to think of this as a division bar, and these cancel. This one's on top, that one's on bottom. That's how I think about it in terms of the formula. That's how I think. You can think about it however you want to think about it. Okay? But that's how I think about it. I think of this as being on the bottom of a division formula, so it cancels. Does that make sense? I mean, if it were to in fact cancel, it would leave a C, which isn't quite right, but it just helps me keep the formula straight. What about the second part? Good. And notice we have numbers for all 4 of those pieces, don't we? So probability of A is 0.3. Probability of C given A is 0.6. Probability of B is 0.2. Probability of C given B is 0.8. So 0.16 plus 0.18 is 0.34, if I did my arithmetic correctly. I would not trust my arithmetic today because apparently I can't write a 0 either.
No, that's good.
Is it okay? At least gives us an idea of how we use the formula, right? Okay. So let's do another one here. Let's just look at the first problem in the sheet. So 3.1, it's on the previous page. Okay. So in a certain town, there's 11 legal holidays each year, and they have 10 parades each year, and 3 of the parades occur on legal holidays.
No, it just means like federally recognized holidays.
Right.
Some places don't recognize federally.
Like Casimir Pulaski Day in Illinois would not be a legal holiday for the country. Just as an example. But Christmas would be, yes. That would be a federally recognized holiday. That's all it means. All right. We want the probability that there will not be a parade on a randomly selected day, given that the day is not a legal holiday. All right? So let's say our event A is no parade, and our event B is not a legal holiday. So what we want to compute is probability of A given B, right? If I've written down the problem correctly. According to the formula we have, what does that need to equal?
Probability A intersect B over probability.
Okay. We agree so far? Okay. Let's do the denominator first, because I think that one's a little bit more straightforward. It tells you there's 365 days in a year, and out of those 365 days, 11 are legal holidays, if I remember what the problem said correctly. So what's the probability that it's not a legal holiday if you just randomly select a day?
354 over 3.
Oops, 354 over 365. So that'll be in the denominator. We agree with that? Okay. So now we need to do the top, and the top is where it can be a little bit more confusing. Remember in the first example that we did to start off this section, we did rolling an even number and rolling a 2. Well, rolling a 2 is the same thing as rolling an even number. So it's a piece of rolling an even number. So to do 2 and even number, we just had to do 2, because it was a subset, right? This one's a little bit different, correct? Because we need no parade and not a legal holiday. Well, just because you don't have a parade doesn't mean it's not a legal holiday, right? We agree? Okay. So, if you're on a particular day, what's the probability that you don't have a parade and are not a legal holiday? Well, let's think about it this way. Well, you already told me how many things are not legal holidays, right? How many things are not legal holidays? 354. Out of those 354, which of them actually have parades on them? 7, right? Because it says 3 of the parades are on legal holidays. So 7 are not, correct? So how many different ways can you have no parade and no legal holiday?
347,
And how'd you come up with that?
subtract 7.
Yeah, subtract the 7 off of them, right? There's a total of 354 non-legal holidays, and 7 of them have a parade, so subtract that off, right? So on top you'll have 347 out of 365. And again, this 347 comes from the 354 minus 7. Okay, again, the 354 is non-legal holidays. The 7 is parades on non-legal holidays. So we subtracted it off. And then if we do the division, or simplify, we get rid of the 365s.
0.98.
Okay, cool. So 98% chance, essentially. Questions on that one?
For this one, would it have been easier to do it the opposite way and then just subtract it off? Or
Do the opposite of
where A is parade and B is legal
I probably wouldn't want to do the parade as legal holiday. Would be a little bit more difficult because of the fact that you're given B, so you'd have to go through a little bit more rigmarole and get around to it and get to it. I think it was more difficult. So I think this way, there's a little bit. I mean, you could have done parade and not legal holiday and did the compliment that way. That's okay? Any questions on that one? Other questions on that one, I should say? All right. Let's see if I can find another one here that's not what I want. Maybe. Let's look at 3.22. This is on the page, it's labeled page 38. The 3.22. So I'll let you read it for a sec. For me, the more complicated the problem gets, as in you start getting 3 or more things, well, definitely 3 things. I think for me, it's a little bit easier to see if I can start with a picture and see what's going on. Sometimes the picture doesn't really help necessarily, but in this case, I think it does. But usually I try to start with a picture just to see if I can get a feel for what's going on this before I start writing formulas down. Like I said, sometimes that's not really possible. Sometimes you just have to start writing down what the formulas are from the information they give you. The reason why I think this one's a little bit easier to do with a picture is because they're actually describing regions in the Venn diagram as you go. Notice that it says for each of the 3 factors, the probability is 0.1 that a woman in the population has only this risk factor and no others. So which regions is that talking about? Yeah.
Each of the diagrams is not intersecting anything.
Good. So each part of the circle is not intersecting any other circle, right? So in each of these spaces, we can fill in 0.1, right? And if we read the next sentence, what does it say? What's that?
Risk factors.
Those three, yeah. So it's telling us about these three spots and not outside of the middle, right? This says the probability that it has 2 and not the third is 0.12. So for each of these three pieces here, we can put in 0.12. So again, the reason why in my brain, which you don't want to get into most of the time, but the reason why in my brain I drew a circle is because as I'm reading the problem, it's telling me how to fill in regions of the Venn diagram. I've got 6 of the 8 regions filled in for free.
There's 8.
Yeah, because there's the one outside the circle.
Oh.
They're all right. So I had to fill all those in for free. All right. So let's see if we can go on now and see if that helps us collect our information. All right. So it says the probability that a woman has all 3 risk factors, given that she has A and B, is a third. Okay, so that's telling us something about how to figure out this missing piece in the middle, right? Telling us something about how to get in there. That doesn't really help coloring it in black with everything else around it black. So maybe I'll circle it in a different color if I'm clever enough. I'm trying to figure that piece right. All right, so trying to figure out that piece is what? If I write it out in terms of symbols, what is that piece that we're trying to figure out the probability of? So A intersect B intersect C, right? Now the problem, in terms of given probability, there's different ways that we could write, in terms of conditional probability, I mean, there are different ways that we could write this. But we're trying to figure out the probability that she has all 3, given that she has the first 2, right? Right? So we're trying to figure out the probability of having all 3. Oops. And in particular, I could just say that what's the probability that she has C, given that she has A and B, right? That's what we're trying to figure out. If we're using the conditional probability formula, what needs to go out in front here? Good, probability of A intersect B, right? Yep. I guess I shouldn't say that's not what we're trying to figure out. We're trying to figure out. No. Anyway, we're trying to figure out the different pieces, and we need to figure out this one. So, what do we know? Well, we know that this piece, they give us this one, don't they? That's a third. Okay. So if I'm thinking about the formula here, we've got a third. What about the other pieces? Well, I don't know this. Let me just call it X. So I would have X on this side. Right? What would go in for the probability of A intersect B now? Yeah, because I got to do both pieces, right? Right? We have to do both pieces, don't we? Because that A intersect B includes both regions, so it has to be the 0.12 plus the X in there. Right? We agree with that? Okay, so now we should be able to solve this. If we distribute the 1/3 through and move things over, you would get 2/3 X equals 0.04. So X would have to be 0.06. Yeah? Everybody okay with that? You just distributed the 1/3 through and shifted it over, and then whatever we have, so just recognize that 2/3 of 6 is 4. 2/3 of 6 is 4, so same thing.
Why are we adding x plus 0?
So this part here is A intersect B, so I have to use this and that. That's why they have to be added together. All right, so we've almost got the entire diagram filled in, but not quite. I've got 7 regions filled in. I need one more, right? So I want to fill in the diagram because still need to answer the question. We haven't gotten to the question in the problem, right? We're just trying to fill in the diagram. What do we have? 0.3 and 0.36 is 0.66 plus another 0.6 is 0.72. I said 0.06. It's 0.72. So this should be 0.28 on the outside. Did I do my arithmetic right? I tend to do it quickly, so I'm not offended if you tell me I'm wrong. At least if you do it nicely. I mean, it might be what you call me after you said I did it wrong. That might be offensive. But telling me I did it incorrectly is not going to offend me.
You did it incorrectly, you good fellow.
You good fellow. Okay, well, see, that's nice. All right, so let's see what they're asking me now. It says, what's the probability that a woman has none of these 3 risk factors, given that she does not have risk factor A? Okay. So, just from the region standpoint, what region are we talking about for none of the 3 risk factors?
Complement of A, union, B, union, C.
Right, it's the outside piece, right? The complement of the union of all of them. Okay. So if I write this as a formula, it wants the probability that she has none of the risk factors, given she does not have A. Yeah. Right? That was I'm just writing it formulaically. We agree with that? So then from the formula, what goes in the denominator? Good. Probability of A complement, right? The thing that's given goes in the denominator. What goes in the numerator? A lot of stuff in this case, right? It's the intersection of the 2 events, correct? So using the formula, it would be A union B union C complement intersect A complement, right? Now, like I said before, in general, I have to worry about the and. But in practice and a lot of problems, often, I'll not say a lot, I'll go back to often. Often, one of them will be a subset of the other. So the intersection will just be the smaller. Is that the case here? Is one of them a subset of the other? Yeah. If you're not in any of the 3, you're certainly not in A, right? You agree? So, I'll change color again to something. That was exactly what I was going for. This piece is contained in this piece, right? We agree? All right, so this will just be the probability of A union B union C complement over probability of A complement. And again, this is because A union B union C complement is a subset of A complement. So the intersection simplifies. And do we have numbers for both of those now? Yeah. The top is that outside region, which was 0.28. What makes up A complement if I go back to the picture?
1 minus 8.
I was thinking about just adding up the numbers, but you could do it that way too. What makes up A complement, what makes up A complement from the numbers? What pieces do I need?
1 plus 1, 2 plus 1, 2.
Good. I need the I want A complement, right? So I want the 0.1, the 0.1, the 0.12, and the 0.28, that makes up a complement, right? Or you could add up A and subtract it from 1. Either way works, right? So this would be 0.28 plus 0.1 plus 0.1 plus 0.12. So it's 0.28 over 0.6. Yeah. Oh, which is what? 0.14 over 0.3. So 14 thirds. So it should be C. Looks like it's 0.267. Was it? Oh, it is. Yeah, it is 467. Sorry. I don't know why I wrote 2. Okay. Now again, the whole reason why I started this with the picture was because I saw the pieces in there that was telling me how to fill in the numbers. So that was why I did it that way. You could have done it just with formulas to start with if you really wanted to.
They're devious. They put in B as the answer for if you just put in A and forgot to add up everything else.
Yeah, that would be. That's why they did that. That was a nice distractor. Yep, I agree. Other questions on this one? All right. One more definition that goes along with conditional probability is the idea of independence. We say that events A and B are independent if the probability of A given B is the same thing as the probability of A. And then you could also reverse that. Probability of B given A is the same thing as the probability of B. So what this means is that the fact that you have the given information didn't change the probability of the event happening. So to give you a straightforward example, I flip a coin. I flip a coin 7 times. Each of those 7 times it came up heads. Given that information, what's the probability I flip heads on the 8th flip? Does the coin remember what you did on the first 7 flips? No. So what's the probability you flip a head on the 8th flip? 1/2. Yeah. That's what the independence means. The fact that I was given that information about the first 7 flips did nothing to tell me what happened on the 8th flip. You see this put into practice at casinos. Believe it or not, you do see this put into practice at casinos. Shockingly enough, there is some probability. See a roulette wheel at a casino. Well, by that roulette wheel, they have a nice little billboard up there for what's happened on the previous 10 spins, typically. So what will invariably happen is that the ball will land on, if you're not familiar with roulette, there's black spaces and red spaces. Half of them are black. Nearly half of them are black, nearly half of them are red, 2 of them are green. It doesn't matter. But what will invariably happen is it'll get on a run where it'll hit black 6 or 7 times in a row. So people will come up and start putting an inordinate amount of money on red, thinking, it came up black the last 7 times, it has to be red this time. No, same probability it was all 7 of the other times, because it doesn't matter. The wheel doesn't remember where the ball landed. Right? But amazingly enough, when they started putting these billboards out in casinos for roulette, they started making a ton more money on roulette. This is what people thought. Oh, hey, it was black 7 times in a row. It has to be red next time. Like a baseball player goes up, hasn't had a hit in 17 at bats. He has to get a hit this time. Right? So he hasn't had a hit in 17 at bats. There's probably a good chance he's not getting a hit in the next at bat. But in general, it's that type of thinking where, well, what happened before affects what's going to happen later, and that doesn't have to happen. So that's what we mean by independent events. In particular, for 2 events A and B are independent if and only if the probability of A intersect B equals the probability of A times the probability of B. You can just multiply the two probabilities together. So as a quick example, and then we'll do some more of these problems on Monday. As a quick example, if you want to draw two cards from a standard deck, with replacement, what I mean by that is you're going to draw one card, look at it, record the result, put it back in there, reshuffle, and draw a second card. Then the probability of drawing two clubs is, well, how many clubs are in a deck? 13. And how many total cards are there? 52. So the probability that you draw a club on the first card is 13 out of 52. And if you put that card back again and reshuffle and draw, did it matter what happened on the first card? No. So it would be 13 out of 52 again, right? That simplifies to 1/16. So it would be a 4 times a 4th. What if you did this without replacement? This is the last thing I'll say for today. Are the events independent anymore? No. Because that second card, the sample size has changed, right? If I do it without replacement, I pull the first card. Are there as many cards left in the deck? No. So they're not independent anymore. So if I want to do this without replacement, club on the first card is 52, right? We agree? Club on the first card is 52. But the second part now is a given probability. What's the probability that you got a club on the second card given that you got a club on the first card? Well, how many cards are left in the deck? 51. And how many clubs are left? 12. So this second part is for the given information. And so you get, if you simplify that, you get a 17th rather than a 16th. So you do the problem similarly. Just one of them is independent, so you don't have to worry about changing anything. The second one is dependent, so you have to worry about changing something. We'll do some more problems with this next time, as well as get into, this was, the independent stuff is in section 1.5 of your text. We'll also get into section 1.6 on Monday, which is, it's still conditional probability. It's just a special case. There's they make a big deal out of it, but it's just a special case. So we'll talk about that next time. Have a good weekend, everybody. Don't forget your homework's due Monday.
Oh, I will.